Okay, so in this lecture and a few more lectures to come will be analog filter design. Okay, so the analog filter design is very important um, for designing the digital filter. With the help of analog filter design, we are going to design the digital filter. So the motivation for analog filter design are twofold. And the first reason is that in digital signal processing or digital processing of analog signals, we do require low pass filters, right? So we have digital processing. In the front end, we may put a low pass filter. Okay, so at the front end to constrain the bandwidth so that the requirements of the sampling theorem are satisfied, right? So when you do the sampling theorem, we know the sampling frequency must be greater than or equal to 2 times of your f maximum. Therefore this low pass filter limits the frequency up to f maximum in order to perform your sampling properly. Similarly, at the far end, we will be having low pass filter. The reason is we need to get rid of high frequencies from the digital to analog converter. So that is the first motivation. Okay, and the second motivation is that our IIR filter design. This is a very important point. It's an important motivation. So IIR filter design, one of the most important and useful in practice, is based on analog filter. So once you have analog filter, then it's very easy to transform into IIR filter, right? So you first design analog filter. So how do you design analog filter? You design the analog filter in the S domain, Laplace domain. Okay, and then transform this S domain into Z domain, because IIR filter design is designed in the Z domain, digital domain. So it transforms from S domain to Z domain. Therefore IIR filter design is based on analog filter using a transformation from S plane to Z plane. Okay, S to Z. So we use a transformation. So the procedure is like this. Okay, so the procedure is like in the first step, we get the specifications of IIR filter. You get the specs of IIR filter and then convert the specs into digital normalized frequency specs. Digital normalized frequency specs. Okay, and then you convert them, this digital normalized frequency specs, to an analog filter design spec. Okay, then from this analog filter design specs, design the analog filter. Okay, so the analog filter is designed in the S domain and then go back to the Z plane. Okay, so in the Z plane you will get the digital filter. So therefore S domain to Z domain is obtained through a process called transformation. S plane to Z plane transformation. So there are techniques which are used to transform the S plane to Z plane. Okay, so the motivation for analog filter design discussion in a DSP course are twofolds. One is we do require analog filter at the front end and at the far end, And a second, a major part of digital filter design is based on transformation of analog filters. See, instead of directly designing the digital filter, it's very easy to design an analog filter and then transform into digital filter, because there is a lot of research has been done on analog filter design. So we have rich set of formulas and design procedures which are available with us. So using that analog design technique, you design the analog filter for the given specifications, and then very comfortably you transform the analog filter design into digital filter design. Okay, so it also is a fact that a discussion of low pass filter is adequate. So even in the analog filter design, no need to design high pass filter, band pass filter, band pass filter or band stop filter. Design low pass filter, that is enough. From this low pass filter you can easily convert into high pass filter, or you can convert into band pass filter, or you can convert into band stop filter very easily. Okay, so as far as low pass filters are concerned, we will concentrate only two types, namely the first one is Butterworth method, and the second one is Chebyshev method. Okay, and the third one is elliptic method. Okay, because in most of the practical cases these two types suffice. Okay, the most optimum filter is of course the elliptic filter. But the problem in elliptic filter is that the design requires numerical computation in almost every cases. It is very difficult to tabulate elliptic filters, and no elegant mathematical formulas are available. And therefore, in most cases, digital signal processing engineers appeal either to the Butterworth method or to the Chebyshev method. But Butterworth is the simplest, but it may involve a little more cost. Cost is slightly higher than the Chebyshev filter. Okay, so it may involve a little, the Butterworth design may involve a little more cost than a Chebyshev filter. Okay, so we will discuss both of them. So in low pass filter design, we also concentrate on only one kind of filter. Okay, only one kind of filter, the so called all pole filter. Okay, that means the filter only has poles in the finite region of the S-plane. Okay, so there cannot be a filter without zeros, but what happens, that zeros will be cancelled with the poles, and finally you will end up with the all pole filters. Okay, so it's when you design a filter, definitely you may have zeros, but that zeros may be cancelled with the poles, and finally you will end up with an all pole filter. Okay, so the number of zeros and the number of poles should be the same for any transfer function. So there are zeros, but these zeros are all at infinity. Okay, so the transfer function we denote by capital H A of S. Okay, and this A indicates analog because we are considering analog filter, and as I said, this is a all pole filter. So in the numerator, let's say I would have constant, and in the denominator s to the n plus a n minus 1, s to the n minus 1, so on so forth, plus a1 s1 plus a0. Okay, and therefore all pole low pass would be some constant divided by this polynomial. Okay, in deviation from digital filter transfer functions, if you recall, in digital filter transfer function we always write the constant term as unity. Here we will write the coefficient of the highest power as unity. So what is the coefficient of this s to the n? 1. Because we will write the poles as s minus pi as a continued product, where I is equal to 1 to, let's say this is a nth order polynomial n. So n number of poles I will be having. For example, if you take a simple polynomial second order quadratic equation, quadratic equation s square plus 5s plus 6, then if you solve this, s plus 3 times s plus 2. So therefore I have two poles, one is at minus 3 and another one is at minus 2. Therefore I can write this polynomial as continued product of s minus pi, where I is equal to 1 to 2. So that the highest power has a coefficient of 1. See, in this what is the coefficient? 1. What is the highest power? 2. Similarly, here the highest power is n and the coefficient of s to the n is 1. In order to write as a continued product, that is the reason we keep the coefficient of the highest power is 1. And this is my constant a0. Okay, what is this constant term? This constant term will be simply the product of the poles p1, p2 up to p number of n. For example, if you take 6, this 6 is nothing but product of two poles. What are the poles? Minus 3 and minus 2. Minus 3 times minus 2 is equal to 6. So you will get back this. Therefore, this constant term indicates product of poles. Similarly, this an minus 1 is nothing but summation of all poles p1 plus p2 plus p3 and so on and so forth. Therefore, our aim there is to find an h a of s, which is some constant. Okay, so let me call that constant a divided by the denominator polynomial. Let me denote by d of s. What is d of s? D of s is this guy. Okay, so d of s is equal to s to the n plus a n minus 1, s to the n minus 1 plus e plus so on so forth, plus a1 s to the 1 plus a naught. Okay, therefore d of s, denominator polynomial of the form s to the n plus a n minus 1 s to the n minus 1 plus and so on so forth, a1 s plus a naught, in such a manner that the given specifications are satisfied. So what are the given specifications for a low pass filter? Low pass filter, if you draw the low pass filter, it has the pass band and it has the stop band. Okay, so let me call this is my magnitude, y-axis magnitude and the x-axis omega, analog frequency in radians per second. Okay, and the maximum magnitude is normalized to 1. This point is 1 and delta p is the pass band attenuation and 0, and this is the pass band frequency omega p. So 0 to omega p is called pass band and this one is omega s. Omega s to infinity is stop band. Omega p is a pass band edge frequency or simply pass band frequency. Omega s is simply called stop band frequency. Okay, and so we use capital omega, okay, for denoting the analog angular frequency. Okay, and this is the starting point of your stop band omega s, and the difference between omega p and omega s is the transition band. Okay, so omega p to omega s is called transition band. And there is a limit, okay, how much you can permit in the stop band, and that is called delta suffix s, and this is called stop band attenuation. Stop band attenuation. Okay, and the range, what is the range? See, this point is 0 axis and this one is delta p, and this width, this is called tolerance. The height is called tolerance. Okay, and this height, what is this height? This height is called tolerance in the stop band. Similarly, this height, what is this height? This is 1 and this is delta p, and the difference is 1 minus delta p, and this is called tolerance in the stop band. And delta p is pass band attenuation. Pass band attenuation. So typically what will be specified is omega p, then omega s, delta p and delta suffix s. From these four specifications, you will have to determine an HA of s, the transfer function. Okay, and this transfer function satisfies these specifications. So this satisfaction of specifications also has to be explained. Okay, so you may not be able to exactly satisfy the specifications. Okay, and you can take liberties with the stop band but not with the pass band. Okay, so see, the specifications are given. Using that specifications, you need to find out the transfer function, but in the process of finding the transfer function, it's not that much easy to satisfy the specifications completely. So in that case, what you will do is you take some liberties with the stop band but not with the pass band. Okay, many of the textbooks say to the contrary, but the practical design experience is that if take liberties with the pass band, you spend more man hours. Okay, you spend more engineer hours in designing the filter. Okay, because the pass band is sacred. So pass band is sacred, but the stop band you can take liberties. Liberties means what? You can over satisfy. Over satisfy means what? This is pass band and this is stop band. Okay, and omega s. Over satisfy means you can bring to the left hand side. Okay, you can bring the omega s to omega s dash, or you can reduce this attenuation to a lower level. That is also good one. Okay, originally it is this much height. Now you can reduce the attenuation to the new level, this level. So that is called over satisfaction. So you have the liberties in the stop band, but you cannot go down like this. It's very bad. Okay, so you will try to bring up to this point. This is my pass band attenuation. So if you bring to this point delta p dash, it is good. If you bring to delta p double dash, it is bad. Therefore pass band is sacred. So don't touch the pass band, but you can play with the stop band. Either you can bring this omega s to omega s dash to the left hand side. Don't go to the right hand side. Okay, bring it to the left hand side, or reduce the pass band attenuation as much as you can. So this is called over satisfaction. Okay, you can over satisfy. So that's what we mean by take the liberties in the stop band and don't touch the pass band. What did I say? Yeah, take the liberties in the stop band and don't touch the pass band, because pass band is sacred. Okay, that's what if my stop band starts earlier, I am happy, isn't that? Because I over satisfy this stop band. So our job is determine HA of S which satisfies these specifications. Okay, so that's it. So that's all about the introduction of our analog filter design. So from the given specifications, we need to convert into analog filter design. Even in the analog filter design also, we will be primarily interested in low pass filter design. Okay, so we will design the low pass filter, and from the low pass filter we can transform into high pass filter or band pass filter or band stop filter or whatever the filter you want, and from there you can transform into the corresponding digital filter using transformation techniques. Okay, so let me stop at this point. In the next lecture we will start Butterworth filter. Thank you very much.